So section 6.3 deals primarily with the logistic equation. But before we actually get to the logistic equation, there's a technique that is used in solving the differential equation that results in the logistic equation called partial fractions. And it's worth discussing here so that we can follow what's happening when we actually look at that logistic equation, differential equation solution. So we're going to start with these two rational expressions. They each have a linear denominator, and we want to add them together. So just as a nice review, why don't you pause the video and add these two rational expressions together, simplify the numerator, and see what you get. Alright, so as you did that, hopefully you found the common denominator was these two linear denominators multiplied together, and the 4 needed an x plus 3 factor and the 1 needed a 2x minus 1 factor. And once we do that, we can distribute and then combine like terms. And we get 6x plus 11 as our numerator. So notice that we started out with just constants as our numerator, and we ended up with a linear numerator. Okay, so really what we're going to do with what's called partial fraction decomposition is we're going to start with a problem like this, and we're going to split it up into a sum of two rational expressions. All right, so we're going to undo that. So here's what we're going to do. We know by looking at this pattern that anytime we have a linear numerator and two linear factors in the denominator that are decomposed, I guess, numerators are just going to be constants. All right. So we're going to call those constants a and b. So we're going to break up that denominator into its two linear factors, and we're going to create a sum in between those, and we're going to say, okay, well, if we do this, then what would a and what would b be? Right? And then we're going to multiply through by the lowest common denominator. Right? So we get this equation that relates our initial rational expression with this decomposed sum, and we get it in this form. Now, the idea here is that this relationship should be true for any and all x values. Okay, so we're going to pick convenient x values that make it easy for us to solve for a, and then that make it easy for us to solve for b. So in picking your x values, think about if I let x equal -3, this entire term, well, of course, this part in the parentheses would become 0, so this a term would be eliminated, and then I'd have 2 times -3 minus 1 times the b equals 6 times -3 plus 11. And it would get rid of the a for me, and it would allow me to solve for b. So that's what we're going to do. We're going to first let x equal -3, and then the term, or the factor that a multiplies by becomes a 0. We can work this out and then solve for b, and we can get b equals 1. Alright, so we've got half of our answer right there. We can do the same thing to solve for a, but if you look at the term of the factor that's multiplied by b here, we need to figure out what would make that equal to 0 to get rid of the b so that we can solve for a. So here we go. Okay, well, I need, what do I need? I need a 1/2. If I let x equal 1/2, then this term here in parentheses, that factor there in parentheses, is going to become 0. So I do that, I plug in x equals 1/2, I can solve for a, and I get a equals 4. So there I have my two numerators, and now I'm going to fill those in up here. So a is the way I wrote it up here was a was the numerator for the 2x minus 1 denominator, and b is the numerator for the x plus 3 denominator. So when we do partial fraction decomposition on this expression, I break it up into its two denominators with a sum, and I end up with a 4 and a 1 in the numerators. Right? So it's a reasonable question to ask, why would I bother doing this? And to answer that, think about these two problems and which one you would rather integrate. Would you prefer to integrate a linear over a quadratic, or would you like to integrate a constant over a linear? Think about the pattern that this would fit into really easily for us in order to integrate that.